Thank you for joining us. There will be Q&A after the presentation, so feel free to submit questions during the session. Then join us in the breakout lounge for in-depth conversations with our speaker and to network with other attendees. Mo Abu Ali is the CEO and managing partner at IoTco, the Internet of Things company. He is a strategic and transformative technology and business management leader with a 20-year record of achievement driving sustaining change in manufacturing. Mo serves industrial and manufacturing clients in automotive, aerospace and defense, and others, providing digital transformation, industrial IoT, and predictive analytics technology and services, as well as an IoT academy for training. Welcome, Mo.
Shannon, thank you so much for the introduction, and thank you for the opportunity to be part of your event again. My topic for today is a zero downtime, zero defect manufacturing operation, and the type of tools and technologies around industrial AI that could help companies realize that vision. Before going into the presentation, very briefly, we are an organization of manufacturing consultants. We all come from manufacturing. We serve manufacturing. I personally have had the privilege of working at Toyota Manufacturing for many years. And most of our organization comes from automotive and aerospace. As Shannon alluded to briefly, we serve industry in 3 ways with 3 practices. We have an academy for Industry 4.0 training, education, and consulting. We also partner with universities to actually teach Industry 4.0 to students. And we then provide a turnkey solution around industrial IoT and predictive analytics. My focus today is an education around industrial AI and its application specifically in manufacturing. And I'd like to touch upon these 3 topics here. Again, if you come up with any question during the time, I'm going to pause at the end to answer as many questions as I can. But feel free to drop in your question as soon as you think of it. So just drop in your question and I'll do my best to address it. I'm covering 3 topics. We always like to start with the business case. Technology is secondary to the business case you're trying to achieve. So what is the business case around industrial AI and kind of setting the stage for predictive analytics today in manufacturing? I'd like to then talk about some industrial AI technologies and solution templates and use cases for implementing AI, again, with a vision of a zero downtime, zero defect manufacturing operation. And then I'd like to give some concluding remarks and maybe highlighting how AI and analytics can actually be deployed in a very systematic way, okay? So let's start with setting the stage. So the field of Internet of Things, or IoT, is by no means a new field. It might be a new naming, but IoT has been around for decades. Jet engines flying in the sky are transmitting data when they cruise, when they lift off, when they land. And this data is being used for predictive analytics so that before the jet engine actually lands in a specific airport, there is knowledge about the need of that engine, whether it needs a bearing change or some type of critical component within that bearing. So the field of IoT has been using the internet in many industries, but primarily in safety critical industries, monitoring in aviation, monitoring in power plant, power gen operations, and so on. And now moving into the commercial sector as well. I have a Nest thermostat at home. It senses when I leave my house and start driving away from my home, and it fluctuates the energy in my house, trying to help me save energy, right? That's a great example of an IoT device. But if we look at the field of the industrial Internet of Things, which is my focus today, if you look at a factory operation, there are multiple layers. There is your machine layer, your asset layer, or your sensor layer. There is your SCADA, which is your data acquisition layer. There is, in some cases, MES, which is a manufacturing execution system layer that is tying data from the factory floor to the ERP floor, right, or to the ERP top floor. And therefore, you have the Industry 4.0 movement, which attempts to break the silos in those sometimes fragmented IT systems within the organization, and then start using the data in a new manner, right? Using the data with advanced intelligence to convert that big data to smarter data and actionable data that can provide intelligence to the end user. And when we talk about an analytics strategy, right, using AI, using digital transformation, we are always recommending to have 4 key pillars in mind. And I like to start from the right and go backwards. So starting with the ROI in mind, what is the business case today of applying AI and predictive analytics in your business, right? And I'll show some examples of that. Once I have an understanding of that business case, and whether it's related to improving uptime, reducing spare parts, reducing quality issues, I then talk about, am I connected? Am I receiving data that allows me to deploy AI and analytics on the factory floor today? And do I have a data lake? Are my machines new? Are my machines too old? Do I need to sensorize my machines, right? So what is the connectivity readiness of the operation to allow us to embark on the analytics journey? And when we talk analytics, and in this presentation, I'll be discussing predictive analytics in detail. I'm talking about looking at the health of the machine, predicting remaining useful life of future failures on that machine. We will talk about diagnostics, actually diagnosing the root cause of the failure of that asset, right? And then lastly, keeping in mind a think big, start small type of mentality, we talk about technology, right? How scalable is this solution? What's the architecture behind it? And if I can prove this technology in a smaller scale, what is the internal and external needs to kind of roll this solution out plant-wide and also enterprise-wide to multiple manufacturing operations, right? So 4 key pillars of an analytics strategy that we should keep in mind when formulating our AI strategy for the business. And I'd like to start with the business case and then going into the technology. So if you look at a factory operation today, a key metric to measure performance is usually your overall equipment effectiveness metric, your OEE. And that presides or that represents your availability, your uptime, your performance, the speed of your operation, speed of making your parts, and quality, right? Goods and bads and the quality characteristics. So part of many surveys out there by National Association of Manufacturers, McKinsey, and many others, the use of predictive analytics and industrial AI in the market today has provided at minimum a 5 to 10% OEE gain, not to mention improvements in labor productivity by automating processes and by allowing more intelligence to be applied on the data versus maybe more paper-based approaches, more manual ways to analyze the data, which are more error-prone and more time-consuming. And then when we talk about predictive maintenance in itself, the idea of moving from a reactive mode of doing something to a predictive and preventive mode of doing something allows you not only to improve your uptime, but to sustain high levels of uptime. I mean, when I worked in the automotive industry, we were running lines at 95% OEE. That's high OEE. That's best in class. But nevertheless, when the lines do fail, they are mission critical to the operation. You stop making cars, right? And a minute of downtime was thousands of dollars, right? So the message here is, you know, running lines at 95% OEE is great, but how can I sustain that high level of uptime within my manufacturing operation? And then maybe it is an underestimated use case, but actually optimizing spare parts. There are manufacturers that are able to reduce spare part inventory significantly because they are actually able to understand when machines are gonna fail before they fail, and then interfacing with their spare part system and reducing spare part inventory by being able to order the right spare part at the right time prior to machine failure. So by using industrial AI, many manufacturers have been able to reduce their spare part inventory and actually close the loop with their maintenance environment. Many manufacturers are running systems like SAP PM and IBM Maximo and other systems, right? And those systems are usually detached from the operation. They are more manually driven systems. So by taking predictive insights and tying them with your maintenance system, you provide a heads up not only to order a spare part, but to optimize your maintenance activity, to schedule a maintenance person to fix the machine before it fails, to reduce your overall mean time to repair, and to improve your mean time between failure, right? MTBF and MTTR are two key maintenance metrics that you want to impact positively by using industrial AI. We've seen manufacturers that have completely optimized maintenance where they've eliminated overhead maintenance shifts. So weekend maintenance, Saturday, Sunday, no longer. They're able to actually cut those out by using predictive insights and optimizing maintenance activities. I'll show a case study at the end around predictive and prescriptive quality, where in a scrap-rich manufacturing process like casting or injection molding, where scrap rates can be higher than normal, detecting and reducing waste at the source by using AI techniques allow you to actually reduce scrap and deliver very strong value to the business. 1 to 5% scrap is a huge ROI for many manufacturers, not to mention the ability to reduce warranty claims and traceability issues by being able to predict defect at the source before the defective part may slip down the value stream, or before the part may go to the end user, which becomes a traceability problem. So business case first should be the approach to any industrial AI and predictive analytics strategy. And business case first mindset allows manufacturers to think of a zero downtime, zero waste mission and vision of operation, and lay out a phased approach to enable them to get to that level of digital maturity and maintenance maturity. These are two quick examples, and I'll be showing them in the case studies, but just to start with a summary. The first example is focusing on industrial robotics. This is an automotive organization that was able to use predictive maintenance on robotic and CNC machine assets. And they were able to detect machine failures early with a high prediction accuracy. And they were able to interface with the spare part system, allowing them to reduce spare part inventory and actually optimize the use of spare parts. It's important also to keep in mind the velocity and the rapidity of deploying solutions today in the market. There are many solutions out there that can help you with the right skill sets to complete AI deployments in a short period of time, maybe 8 to 12 weeks, and to use those templates within your center of excellence environment, and in some cases, autonomously roll them out across your organization. In the second case that I've started to allude to briefly, in the high pressure die casting industry, industry norm for scrap could anywhere between 9 to 15%. So just imagine I have a mid-sized casting company doing aluminum die casting, right? And I'm making parts every 10-second cycle time. And my industry normal scrap rate could be 9 to 15%. I mean, that's a high number, right? But it is kind of a dirty manufacturing environment, and scrap rates are high. But by using industrial AI and making a correlation between the process parameters of the casting cell and using them to predict good and scrap on the machine, and in some cases automatically segregate the parts to good and bad by using AI, and by doing decision-making and analytics within less than 10 seconds, such organizations can utilize what we call the power of 1%. 1% scrap reduction in a casting company is around $250K per plant per year in savings, right? So the message here is, maintenance 4.0, quality 4.0, industry 4.0, powered by industrial AI and machine learning based analytics. Where is your business case, right? What is the why for your business, and where should you start to deliver the quickest wins for your business using industrial AI today? So I'm going to show a few examples, okay, technical examples, a high-level technology conversation, and I've picked 3 case studies that center around the business case conversation I just showed. And then I'd like to summarize some recommendations on using industrial AI in manufacturing in a more effective manner. So let's start here. Whether you're looking to improve uptime or reducing scrap or improve spare parts, the vision is really about a worry-free manufacturing process. And a worry-free manufacturing process is about improving maintenance and reducing scrap significantly in the manufacturing environment. And when we look at a general 3 layers of any industrial AI predictive analytics solution today, it starts with data. It starts with getting connected. It starts with a data lake of some sort, okay? And then it goes into an industrial AI type of solution or platform that is able to digest that data and convert that data into use cases for the business, right? So if we look at the left side of this, I'm getting some asset data, maybe data from the machine controller, from the PLC, maybe add-on sensors like vibration may be required to be added to the machine. Process parameters that I might need to capture from a SCADA system or another type of solution in the area. Quality type of data, right? Whether it's captured with a camera or an X-ray machine or a thermography image, whatever that might be, right? And then this data is ingested, digested, converted to useful information and metrics using AI, and we'll talk about how this is done. And then delivering those use cases for the business, right? Telling you predictive metrics of what is the true health of your asset. Is this asset healthy to continue running without interruption and to continue making good parts? What is the remaining useful life of the asset? What is a prediction window of when this asset will fail with a prediction accuracy? And what is the diagnostics, right? Is it my third axis, my third joint on my robot failing? Is it the bearing in my spindle having an inner race failure or an outer race failure, right? So this is a predictive maintenance use case. And then with the correlation of the quality data, such as the casting example that I've talked about, we're starting not to talk about the machine health, but we're talking about the part health. Is this aluminum cast predicted to be a good part, a suspect part, or predicted to be a bad defective part that I have to segregate or reject from the machine, right? And it doesn't have to be an aluminum cast. It could be a semiconductor chip that you're making on your fab, right? It could be any type of production part, right? Be it a discrete manufacturer or a process type of manufacturer. And then we're talking defect prediction and diagnosis, right? Why am I rejecting this part? Is it due to a temperature and pressure fluctuation that pushed my model, my AI model, to make the decision to actually reject that part? So what is the diagnosis? What's the root cause of predicting a quality issue on this machine or on this part? So the data lake, are you connected? Do you have the right data today to do industrial AI? This is the foundation for any AI and analytics project. Good data. Good data drives good analytics and more accurate, precise predictions over time. And then going here, it's a 6-step approach. It starts with data collection. It goes into processing that data using machine learning algorithms to cleanse that data, to remove outliers from that data. It goes into feature extraction, which are these statistical indicators that include time domain analysis, frequency domain analysis. There's a wider set of feature extraction and reduction of dimension type of analytics, right? So I'm taking data, converting them to feature sets, and then using those feature sets to train an industrial AI algorithm that tells the end user 3 things. It tells the end user, am I drifting away from my baseline? What is my health? It tells the end user, what is a prediction with an accuracy of a failure on this machine or component, okay? And it's telling me a diagnosis, right? And there's a lot of machine learning algorithms out there, but when it comes to specific manufacturing templates, over the many years, decades, those algorithms have been well studied, well documented. The literature is in place. There is no need any longer to trial and error solutions, okay? So if we look at a manufacturing environment, you are looking at many different types of key processes. And these processes have been studied and have been documented, and there are solutions out there that deliver quick value for these critical assets. So if you have industrial robotics and you want to do prognostics and health management or predictive monitoring of the joints of the robot, right? There are solutions that can tell you that axis number 3 on the robotic is going to fail in the near term, order a new spare part. If you're looking at a CNC machine tool, the spindle bearing using vibration-based analytics, or the ball screw, the linear guideway of the machine, using data that comes from the controller, or the actual coolant of the machine, so the lubricant on the machine that may degrade, and the degradation of that liquid may lead to an issue with the machine or an issue of the part that is running on the machine, right? There are sensors that can give you the chemical characteristics of the coolant. Advanced processes, we talked about casting. It's a big data project. It's like 80 process parameters coming from the casting machine. Stamping presses, not just using vibration, but actually acoustic sensors that listen to the sound of the press. And from the sound of the strokes and the hits of the press, you can actually infer and learn the sound of a good hit on a good part versus the sound, the harmonics of a bad hit on a bad part, right? So it's a non-intrusive way to listen to the sound emission acoustics of a stamping press and make recommendations and diagnostics on the machine and the part. And then you have your surrounding equipment, right? You have pumps that control the line, you have chillers and compressors, you have motors and gearboxes, right? So the idea here is a systematic approach and solutions that can be deployed with connectivity and with the data model understood, right? So what are the parameters that I need to get from a robotic or a CNC machine or the stamping machine? There are well-studied data models, right? That's sometimes you call it a data map. So now that I know my data map, what are the algorithms that it needs to run through? What is the analytics workflow from signal processing to features to health to prediction to diagnosis, right? And how quickly can I deploy those solutions? Could it be done in weeks? Or am I running solutions and trying to trial and error 6 to 12 months to get these solutions ready for my business, right? And what is the ROI behind it? And how can I have analytics as a service to deploy these templates factory-wide or to deploy them company-wide? So usually the implementation frameworks for any predictive solution look something like this, okay? And this is a high-level picture. It is really 2 sources of data. There is machine controller data, if available, and there are add-on sensor data, if required to be added to the machine. And then there's an aggregation layer, okay? So sometimes edge analytics or edge AI are done in the factory, which is some algorithms to take machine controller data, aggregate them, and then convert them to features to reduce the bandwidth and to reduce storage and things like that. So there are some things that can be done, quote unquote, on the edge. And then the data can be sent out to the cloud. This could be the private cloud of your company, or it could be a public cloud like AWS or Azure. So if you look at the general implementation framework of any industrial AI solution today, it all starts with connectivity. It all starts with it goes into the aggregation layer, and then it goes into the representation layer, which is your server cloud infrastructure, and then the user interfaces that go beyond that, okay? So keep this architecture also in mind, because when we're talking about technology scalability, right? Maybe I can make this architecture work for 1 factory, 3 machines, but what is it going to look like if I have 100 machines in the factory, or if I got 10, 20 plants in my manufacturing operation? So let's quickly talk about some solution templates. Number 1 being industrial robotics, okay? The message here is that predictive maintenance will not solve all your problems, right? Industrial AI and predictive maintenance are usually targeted towards specific failure modes that are effective for those types of algorithms, right? And this is a great example for an industrial robot. You have motor brake failures, you have gear backlashes, bearings issues for each of the axes or the joints of the robot. But if you have a cable failure, if you have a dead battery, an electronic type of issue, those are preventive maintenance type of things to be done and fixed with a good PM type of system, a time-based approach to fix those issues. But predictive maintenance is not geared towards that. So it's important to understand, what am I trying to achieve technically? What are the failure modes that I'm going after? And can AI and predictive analytics support me on those failure modes? So that's an important part of your solution template. And then the second important part is solutions that can also be agnostic. So I have a Fanuc robot, I got a KUKA robot, I got a Denso robot, right? I got new robots, I got old robots. So how can you make sure that the connectivity is standardized, harmonized? And how can you make sure that your solution can work with a variety of manufacturers and a variety of ages, right? And then it's very important to intuitively view the solution at the end of the day, because the end user is not a PhD, is not a data scientist, right? The end user is a professional maintenance person who needs to understand machine health, prediction of failure, diagnosis in a very intuitive way, and use those systems without needing to have in-depth technical knowledge of algorithms and machine learning and things like that. So the HMI, the human machine interfaces of using industrial AI solutions today, is actually key. It's not just about technology, it's about technology, process, and people. Technology, process, and people enable these solutions to be adopted and used by the organization. And this leads to ROI. I won't go through this. I think I've discussed business cases quite enough, but just imagine a solution for industrial robots at an automotive factory. This is a real ROI calculation. Significant 1-minute downtime cost. 30 robot failures happen every year. If the predictive solution only captures 50% of them, this is actually a huge ROI for the organization, right? So how can I move from a reactive, time-based approach to a predictive, preventive approach, and keeping technology, process, and people in mind? CNC machines, complex piece of asset. You got tools, you got spindle bearings, you got feed axis, you got coolant, right? How can industrial AI support me here? Well, it starts with data. It starts with understanding, what data do you need to capture from your controller? What data do you need to capture from add-on sensors to the machine, right? I need vibration on my spindle bearing. I need to use motor current, feed rate, and speed on my dresser, my feed axis, for example. And again, I need an intuitive solution that is able to assess health, predict my bearing failure, and then tell me that I'm going to have an 8 kilohertz band frequency of failure, right? I'm looking at a component and I understand the geometry of that bearing, and I can actually diagnose using industrial AI that I'm having an outer race failure or an inner race failure or a ball failure on the bearing, right? So again, it's important to go from data to analytics to human machine interfacing, the people side of it, in a way that facilitates the adoption and usage of those solutions. Concluding with casting. Casting is another complex example. It's a big data project. You have 50 plus data parameters that are captured from a complex piece of equipment, a lot of moving parts, a trim press, a die heater, an ABB robot, a dosing furnace, right? You got pressures and airflows and temperatures. Machine has shots, right? Every time it injects molten aluminum to make a part. So how can you take that data and convert it into an operator user interface that provides predictive quality metrics for every shot, every die open event? Within 10 seconds, a new part is casted. So within less than 10 seconds, you need to make a decision and correlate the 50 process parameters to whether this is predicted to be a good or a bad or a suspect part. Green, yellow, red, as you see here on the sample HMI, right? So it's important to, when building a quality 4.0 type of solution, to understand that this is not about the machine anymore. It's about predicting part defect issues and prescribing a decision, right? Feeding data back to the machine to command the machine to do something. Pick up the part, put it in a reject bin, or pick up the part, put it in a good bin, for example. So fast decision-making using industrial AI in a big data application setting like high-pressure casting. So what's the conclusion here? The conclusion is, a lot of folks start from thinking about the technology. What algorithms do I need? What templates do I need? How do I manage my data? I mean, it's great. That should be part of your strategy. But it's actually more important to start here, right? How is my process designed? Do I have the right team structure, right? A multidisciplinary team. What are their skill sets? What's the people side that needs to support my industrial AI project? Which factory is ready to adopt this, right? This factory may be more mature than others. So what is the digital readiness, digital maturity of the organization to embrace those technologies? If we understand the people and the process side of it first and select the right area to pilot those solutions will truly flourish and will quickly add value to the business. So we have an approach we follow, and this is a very systematic approach, actually. I would recommend this approach to manufacturers out there. Think big, start small, as they say, but also fail small and succeed small and prove value and scale fast. You have to do an assessment. You have to understand your business case. You have to do technical workshops that map out the gaps for your people, process, technology, and then where should you start would be the answer. Deploy a proof of value, run it for a 2 to 3 month period of time. Don't go longer. If it's going longer and it is not delivering your business case, think about understanding the reasons why, and think about pivoting or finding a way to, maybe it's a different plant, maybe there's an issue with the people or the process or the technology. Find that out quickly, pivot, and redo your proof of value. And then start thinking about training your center of excellence environment, your COE team, right? This multidisciplinary skill set team that can take out the results and lessons learned of the proof of value and can actually scale that template across the organization. Even they can do it themselves. So in conclusion, digital transformation and analytics is a journey. It's important to act now. It's important to make it operational. And when you make it operational, make sure the technology backs your business strategy. Business plus technology equals a proof of value that is truly adding value to your business. That immediately becomes part of your zero downtime, zero defect vision. And make sure you start at the right place. There is always readiness and maturity that is contingent upon your people, process, and technology. And your benefits will truly only accrue as far as the weakest link. So start at the right place at the right time, and you'll surely be successful in implementing industrial AI to support your business strategy for your organization. Thank you. Happy to answer a few questions. So Shannon, I believe I finished right on time. I do see a question that was posed by A.O. Smith. Do you have any solution templates relating to welding applications? So in fact, yes, welding applications are well studied. It depends on the type of welding application. There are spot welding applications. There are interesting laser welding applications where it could be actually a good predictive quality candidate because the degradation of the laser itself on the operation may impact the quality of the weld. So yes, we do see a lot of welding related applications. And I think there is a play there, not just for predictive maintenance, but actually predictive quality and the actual quality of the weld, which may be impacted by the degradation and the process itself. So happy to, if you shoot me an email, I'm happy to maybe share with you a few case studies there and have a conversation there. I'm trying to answer the questions on my cell phone. Sorry, I'm trying to read them. There is a question that says it fits well for mass production cases. For example, the automotive application I showed you guys. How about non-mass production fields? I think that's an excellent question. What I did not really talk about today is the smart connected product side of our business and knowledge, but surely there are applications in ships, there are applications in shipyards, there are applications in train or locomotive systems. I'll give you a short, cool example in a train. You know, the doors, right? The thing that could degrade the most is the doors because they keep opening and closing all the time. So we actually did a project to measure the degradation of the door of the train because there's always service calls related to the door and even the elevator itself, the door of the elevator. So imagine the bearings and the motor that control the doors are being sensorized, and we're using that sensor data and analytics to have a just-in-time predictive and spare part replenishment tool to measure the degradation and predict the defect of the door on the train, because that would lead to customer dissatisfaction, right? If the door on the train stops working, you could actually delay the train, right? So that's just an example. But I'm a believer that some of the templates I've shown, like the critical components, the gearboxes, the motor, the pumps, and all that, they're very relevant to those connected product application, and they could be applied in any industry, because there's always an issue with uptime or quality or spare parts or customer satisfaction, right? And that entails the use of industrial AI to solve that problem. So happy to have more conversation with you around that. Last one, maybe. We have islands of automation, and I believe our next step is putting data IoT architecture to aggregate it, present the data to enterprise apps. Would you agree that this is a good next step? So I am a believer in a strong IT-OT relationship. I see many companies that form a digital steering committee. I really appreciate the way they do that. It includes representatives from IT and also representatives from the different plant. So there is the voice of the business and the voice of IT working together collaboratively. I do agree with you that you have islands of automation, silos of data. It's good to build a connectivity layer, a harmonized layer that is able to standardize that communication within the plants and within multi-plants. And then once you have that standardized approach to get connected, you need to provide that data to a representation layer. You can provide it to an OEE system, an MES system, an IoT system, but the same data lake or part of it can also be used for predictive analytics, right? I'm not a believer in those who might create multiple data lakes and they say, this is for my predictive, this is for my OEE, this is for my MES. I actually see that the data lake could be built in a harmonized way, and the data maps are known for each of the templates, and then you can plug different IT systems to interoperate with that data lake. So the digital steering committee part of it is important, and the standardized data lake approach is also important for the business. We do this a lot as part of our IoT Academy. Happy to have that conversation with you offline. So I think this is all. These are all the questions I received, and this is all the time I have. Shannon, do you want to take over?